So in the meantime, while people are joining, I'll quickly introduce myself. I am Nayan. I work as a data engineer DevRel at OLake. And joining us today is Lester Martin. He's developer advocate at Starburst. Lester is a data engineer and developer advocate with over a decade of hands-on experience across data pipeline, data lake analytics, and distributed query engine. At Starburst, he focuses on helping engineering teams adopt Trino and understand how query engines interact with open table format like Iceberg. He also regularly publishes technical deep dives on Iceberg internals. And really glad to have you here, Lester. If I have missed anything in the introduction, you can jump in and you can introduce
Just
yourself
a
as well.
heck of a nice guy. Glad to be here. So thank you for that intro.
You're welcome. So, if any one of you is new here, OLake is an open source data replication engine that syncs data from databases Kafka and S3 into Apache Iceberg. We support both full load and CDC for continuous updates. OLake is built for high throughput ingestion. We deliver up to 3 to 500 times faster sync at a much lower cost while keeping your lakehouse fully open and portable. Today, me and Lester, we are going to walk you through how you can go from a raw database changes to fully queryable Iceberg tables. This is not just going to be a theoretical session. Instead, we will be focusing more on live demonstrations. So let me quickly share my screen in here. So, yep. Yeah. So first, let's talk about some problems that people are facing currently. So first problem is the scaling problem. Most existing ETL tools work well for small scale data, like if you want to ingest small in some GBs or a few TBs, but as the data grows, things become pretty hard. These tools are actually warehouse centric and are not built for modern data lakehouse architecture. And in real world scenarios, we are dealing with multiple sources, not just one. We have streaming systems like Kafka and large data sets sitting in the object storage. Hence, ingestion becomes a scaling problem. The second problem is complex tech stack. So let's say you have decided to move to Iceberg. At first, it sounds pretty good with all the properties it provides, like ACID tables, time travel. But in practice, the ecosystem is actually complex. It's not that simple. So you will end up having multiple tools, like one for ingestion, one for streaming, one for compaction. And all of this just keeps on increasing the engineering effort significantly. And, uh, and the main reason people are facing adoption issues is this. And the problem three is vendor lock-in. It is pretty common problem out there. Many organizations already have deeply integrated data platforms. So moving away becomes really expensive and also risky. At the same time, costs keep rising every year. So the teams are stuck in and want the flexibility to migrate, but it is actually painful. So these problems, all of these problems here are solved by OLake. As you can see here, this is actually a small environment of how it looks like. So we have all the sources right here, and in the middle comes OLake, then destination, and then the query engines. So what OLake does is it takes the data from your source and sends it to the destination as Parquet files or Iceberg tables, basically in any object storage. And you can use any query engine that is Iceberg compatible. So you can use Databricks, Trino, DuckDB, Athena, Snowflake, and many more. So the important point comes is it's not just to move the data fast, it's also to make sure that the data is consistent and accurate. So when you are doing a full load from your database, you are dealing with millions or even billions of records. Moving it in a single stream becomes slow and inefficient. OLake has a chunking strategy for each database. It is different, which makes sure that efficient chunks are made and these chunks are processed in parallel, which provides high throughput. We also make sure that these chunks are sized in a way that they provide an optimal Iceberg efficient chunk. For instance, around 500 to 500, 300 MB to 500 MB Parquet files. So we are not just moving the data, but also preparing it for optimal querying. The next issue is let's talk about correctness. Let's say we committed the data successfully in Iceberg, but before updating the file, the state file, let's say the sync broke now because of any particular reason. And this scenario can lead to data duplication as the state is still pointing to the older files. So we have implemented the 2PC feature here that makes sure that even in any worst case scenario, the sync fails, we don't end up writing the duplicate data again. Also, we have resumable full load option, which means if sync fails in between a full load, um, then we do not have to start from the beginning. The state file keeps a track of what all chunks are not synced at the moment. And whenever the next sync runs, we make sure that only the remaining chunks are transferred. So, as mentioned before, OLake supports two primary replication strategies. One is full load and the other is CDC. So basically, you do full load in the beginning when you want to do a complete data replication from your source to destination. But as days passed and your data keeps getting updated in the source, you don't want to keep doing full load again and again because it's an expensive operation. So here CDC comes in. What CDC does is it only captures the most recent changes, be it insert, delete, or update, and makes sure that only these changes are synced to Iceberg. This is ideal for large and frequently changing data sets. This is how a CDC action looks like in Postgres. So let's say you have a table with 3 records, and you want to update the record with ID 101, making the status processing to shipped. So when you do that, your wall log looks like this. So what OLake does is it makes sure to take the after change and sync it to the destination. This is as simple as it is. So next, we'll walk you through a quick demo of how the sync works in OLake. So for this, just give me a second so that I quickly share the entire screen so that I'm able to even show the database and the changes there. I hope my database is visible, Lester.
There it is.
Yeah, thank you for the confirmation. I'll quickly print first the IDs and the fair amount for the first 10 IDs in the table trips 2 that I have. So as we see, the fair amount is 4,800, somewhere in that range. And what we are going to do is we are going to update these fair amounts by adding value 100 to it. We'll run this and then we'll check the changes again in the source database. So now we see the values have been changed. Now what we'll do is we'll go ahead and run the sync in OLake. So now I'll quickly explain you how to set up a job in OLake. All you have to do is click on create job, give your job some name, and you can set up a frequency. Since I already have a job set up, I won't be setting it up right now. After you give your job a name, you will end on the source page. So what you can do here is the source page looks like this. So you can fill your host details, database name, username, password, port, and all the information here. And just in case you want to make sure that you want to do CDC after your full load, make sure to check in the CDC option in the update method and enter your replication slot, your publication slot as well, so that the next time you run the sync, only the new changes get synced, not the entire table. And similarly, you can also set up your destination as well. All you have to do is provide your destination details, secret key, access key, your path, and your AWS region, and that's it. So after you create a job, all you have to do is click on actions and sync now. So when we do sync now, we can view our logs here. So we have updated around, I think we just updated around 10 records. So we should be able to see the same in the logs here. Yeah. So as we can see, the sync has been completed and the total records read are 10. So now, Lester, you can take it back from here and you can start with explaining us how we can query the data on Trino and Starburst.
Awesome. Let me share my screen and show you what I got here. Entire screen, why not? Yeah, that one. Hopefully it'll be up here in just a few seconds. Hey, no, that was awesome. I appreciate that. In fact, I was watching live that table behind the scenes because I didn't know how many files were backing that. And I noticed it went up by 2 instead of just by 1. And I'm going to talk briefly about that as we go along here. My screen is pretty small. The font is not all that big. I get it. But I can try to make it a little bigger if we get some comments or stuff that's out there. Who could talk without a quick couple slides? Why don't you I got 3 slides here. You know, we've been talking about Iceberg, all good stuff, multi-engine, all that great stuff. The gotcha, though, I think the cool part and the gotcha with Iceberg is this mess. And we're not going to try to walk through all this kind of stuff right now, but this is how we're keeping track of things. The fact that Iceberg did put not just these data files, not just those Parquet files out there on the data lake, on your object store, or wherever you're keeping it. We're using S3 right here, but it keeps all that metadata. And in fact, it's keeping lots and lots of changes. Every time we make a change, it's keeping track yet another immutable set of information that kind of lets us know what we're talking about, when, where, why. And I think I have a third slide, because I'm going to talk a little bit about this as we get into it. But a lot of what I'm going to show you is the fact that, you know, we all hear things, this small file problem. And those of us that have been around like 10 years in this space or so probably had a different small file problem with Hadoop. It's a similar small file problem, but it really comes down to this: no matter what, if your data is and many more smaller files than fewer larger files, and we're talking about a system that can handle lots of files, lots and lots of big files. But yes, if you're 10x, 100x, 1000x more files that themselves aren't very big, almost all the engines are going to struggle. Definitely Trino is going to struggle. The gotcha that I would make a point, and I'm going to show you these file sizes in a second, is that when we have a scenario where the changes, either the net adds or changes like you just saw happening there, we are going to end up with smaller files because, you know, these files are immutable. So if I've got a file with 1 million records and I change 20 of those records, without going into all the great details about delete files and stuff, if I update a single record in an Iceberg table, I create 2 more files. I end up saying, hey, one of those records in this big file, I need to capture it. So we build a deletion marker, a small file that just says, hey, get rid of that record. But I was doing an update. So what I need to do, I need to do a kind of like a net new add. Oh, here's a record. So I create this kind of trail of smaller files that happen. And in fact, that's what we're going to go and look at and try to see live here. So let me make sure my system's still running there. Here's that table Diane was populating. You know, it's just trying to truncate it off. It doesn't really exactly matter the data that we see in there, but I just want to verify we can hit it. You know, so 1,000 rows. And we might say, how many records are in there right now? Well, there are 6.4 million records. So Diane, if that's a wrong number, you let me know, but that's the number I see at this point. I mean, well, don't let me know. Maybe that's not good. You know, there we go. So we did a count. 6.4, relatively small table. You know, if we look at it just for giggles in my engine, at least in Trino's side, it's just going to tell us it's a big table. It's going to tell us it's, you know, Parquet files, it's Iceberg format. Choose a format too, and there's the data. It's out there on S3. That all makes sense. Nobody's complicated. Here's where it gets a little more fun. We say, hey, tell me about the files that make up that table. So before Nyan did his last update, there were 55 of these. There's 57 now. There were 55 of these, and there are 57. They're all Parquet files. And if I scroll over here and I just kind of roll down, you start to see funny things like, wait, this one only has 10 records and really small, but they're all about the same. He did an update. And then there's one maybe with 1 million-ish records, just a big one. And you see some of these smaller ones. So these smaller files are likely because either net new adds or they were updates. Hey, change this, change that. So we end up writing often a whole bunch of files. And in fact, if you counted up these numbers, it may or may not come up to the number you saw a minute ago there. So let's see. All right, so if I'm going to look at those same files, why don't I ask? And this is the metadata. So this is, engines have a way, instead of going and look at the data lake and show me all those files, you can ask, usually call them metadata tables or something. That's what we call them in the Trino land. So I said, hey, go back and just rerun it again, but order it by the biggest one. So there's this file with 1 million records, and then like you see a whole bunch of files with 20K, 200K, and then a few files with like 10. Okay, interesting, wild stuff. And just for one more, before we do any magic here, I would say just give me some averages, right? So the average records, average size, and I'm going to capture some of these values right now. All right, remind myself, because we want to see what's happening. So before and after, let's pull it like this off screen. There we go. This one plus this one. There we go. Lester, you can do this. I know you can. All right, average number of records, average number of rows, 207K. What else do we have in there? Average file size, 8.7. 8.7K, was it? 8.7K, I think that's what it said. 8.7 meg, sorry. 8.7 meg. Thank you. And 2 more pieces of data. Min and max. I don't know if I captured those. 786 and 60 meg. 786, 60 meg. So really small one. 786 bytes and 60 meg, I think is what it roughly would have said. All right. And number of files. I know that was 57 because I was just looking at it. And I think this rows up here was 6.4 mils, something like that. All right. Those are some rough numbers. Okay, so I want to actually get some performance characteristics about this. So I was looking at the data this other day, and I said, what's going on here, right? And I said, hey, look, I noticed there was this field called passenger count, and I was curious to how big are the riders, and I found an interesting one. Hey, there are some rides that have 0 passengers. I thought, what the heck is that all about? So I went ahead and just said, hey, let's do a query that it's going to force, based on what's going on, we have to look through everything because, you know, unless with all the statistical information, like we have to look at all the files to kind of find this. So I got something, and that happened, you know, relatively fast. But I said, show me what's going on here. Tell me what relatively fast is. So relatively fast wasn't all that fast. I ended up coming back with this query saying, hey, it took me about CPU time. How much time did we burn on CPUs? A lot, you know, I think a lot, 714 seconds. What was the wall time? 2.83 seconds. Interesting. I'm sorry, that was up here, 2.83 seconds. We didn't get this other one. And some other details, things like splits, if you're familiar with what's going on. How did the engine kind of look at all this? So I'm going to use my tooling. Every environment's a little different. This is Trino's land. And I went to the stage that said, read this stuff. And I can see right there, it actually read, it's used about what they call 28 splits. So we worked on things independently. It was smart enough to realize some of the files, that record of 0 just wasn't going to be in there. So we got a lot of pruning, and that's all good. So I think I said 28 splits. So I'm going to capture that real quick. And I have 2 more things I'll capture real fast. And mainly I'll talk about them when we do the other one and tell you why it might be a lot better. So I'm looking at what they call the query plan. Output. I'm looking at the bottom here. I'm going to say, yep, there was those 28 splits I saw. And I kind of have a new metric I'm learning a little bit about called generation time. How long did it take to generate the wait time in whatever, 30, I'm going to call it 39 milliseconds. That's what I'm looking for. So again, not having anything to compare about won't really matter. 39 milliseconds. And then my average input average row. I want that one again. I think I got that right, about 229K. All right, guys, I'm going to make all this better. 1 second, 229K. And last thing I want to do is this interesting number right here. So there's my 7 seconds of CPU time. But look at this. I've got 29 seconds of schedule time. I'm going to tell you what that is in a minute. So let's see, 29 seconds of that. All right. So we got a problem. Not a problem. We've got a solution. It's working. The reality is we probably want to do something about that. There's too many files. Want to clean them up and that kind of stuff. So I'm just going to use our way of doing table maintenance for compaction. We call that we just call it optimize. It's an old Trino term. It worked for other things as well. But what it's going to do, it's going to go out there and say, hey, I'm going to look for a threshold. I'm going to look at all the files. And in fact, it's looking for files by default under 100 meg. And it's going to say, what do I want to do with them? I want to rewrite them. So this is that notion of taking many smaller files and writing fewer bigger files. but it's doing not just that kind of lumping them together. I was suggesting there are these trails of deletes and adds and deletes and adds. It's actually rebuilding all that information. So that took us about 17 seconds. That's what I think I saw the other day about on this team. It's a one node cluster, so it took longer than you might want to have. But really, I want to say is, okay, what's different now? So, hopefully the number of the rows is still the same. Yep, 6.4. But what might be different is this. Let's go look at the actual files that exist on the covers. Aha, we're looking a little better off. We got 4 files now. So took all that information from whatever it was, 57 files, and rebuilt them, packaged them up into 4 a little bit bigger files. Are they gigantic? I don't think so. They're still some that are good, 78 meg. So it's getting close to that 100 meg kind of sweet spot, at least for Trino. All engines would be happy with 100 to meg to a gig. That's a pretty sweet spot. I'll just compare these other numbers. I'm not going to write all these down. I just want you to see them. The files are, I was looking for the averages, I guess. The files are going to hit right on the money. They're all about average size, average number of records, average file size, 90 meg. That's good. I'll write that one down. That's worthwhile. Average file size, 90 meg, not 9 meg. So an order of magnitude bigger. Yay, that's good. Number of rows, who cares? Who cares? That doesn't matter as much. Okay, let's run that same query again. The one that we use as our kind of our benchmark of was it good, was it bad, that kind of stuff. I'm not sure why it took so long. If it doesn't look that great, I might run it twice. There we go. It looks a little better. I'm going to capture these numbers. So same query, and here, and as we capture them, we'll talk about them for a minute. The wall clock time. The wall clock time was probably not great. It actually took us longer as a human to get it. My hunch is if I ran it again, it would be a little faster. I'm not sure exactly what happened there. But the real test starts to be, especially at scale, when these tables are running much bigger and all that kind of stuff, it's going to be, what did you pay for? What was the financial cost, and what was the deferred cost or the opportunity cost missed because other queries or other activities couldn't run. So the CPU time was dramatically different. And again, this is a tiny little 6 million record, do 600 million, 6 billion, 6 trillion. So it took a lot less amount of CPU time to crank on that thing. What else is going on here? Well, I'm going to dig in. I think I went to the stages and showed you a pretty visual way to find the number of splits, but I'm just going to go to the query plan output, and I'll make it a little bigger for those that need to see text for what it is, like live. One place I can get is right here. It's 4, and it's 4 because there's 4 files, and that's how Trino works. So the number of splits was dramatically different. Why is the other one smaller here than that one? Well, because files have min-max values, and I picked a weird one like 0, and there was a good chance that a bunch of those files didn't have 0 in it. There was only 60 records or something, so it actually skipped a lot of things, which is good. That's pruning. And this other thing, the generation wait time, 12 milliseconds. That's just overall how much time did it burn doing this. This would be dramatically different. It's going to be in relation to how many splits there are. So that's kind of another kind of thing. But there's another value I want you to look at for a second. This kind of tells a story usually. There we go. Schedule 11.6. Schedule, good. 11, let's just say 12 seconds. So what this is this notion of there's some opportunity cost even with the CPU. Trino will tell you exactly how much time it actually spent of CPU, but it'll also tell you how much time the CPU was given to a task to do some work. And basically, it's a little bit more sophisticated in this, but you can kind of say, what's the difference between scheduled and CPU time? And that was time it was blocked. You see here, there was no time that was blocked. That's not exactly true. It was blocked. It was waiting on the S3 and that kind of latency going back and forth in more files. When you get tens of thousands of files, you'll see there's a difference there going back and forth and back and forth. All right, so the good news is it was faster, better, quicker, and that's really kind of what we really, really wanted to see. The average size is, I think, 1.6 mil, 1.6 mil. This is good. It's back to the point of average input 1.6 million. There we go. Generally speaking, what I want to say is this is actually all good. This is what we were hoping to see. And what we really saw, just to kind of wrap my demo up, is that tooling thing that Diane was talking about. Is that good and it's bad? It's good and it's bad that many different tools can interact with Iceberg. I think it's a good thing. Obviously, could you just use one tool for everything? Maybe. And that's all your decisions. But Iceberg gives you lots of optionality. What we showed is a CDC tool loading it. We use another tool for just data analysis. And we went ahead and used that same tool, Trino, for data maintenance. So what we would do is we'd find a way to say, hey, let's kind of couple these things together. And you could build what I saw manually in your pipeline. But what I would suggest, if you were using, here I am being a shill, if you're using Starburst or Starburst Galaxy on top of Trino, you might come in here and just say, you know what, I'm going to create a data maintenance job. I think I have one already out there, right? Yep. Let me kill that one. Oh, no, it's a different one. Yay. So I'd say create you a data maintenance job, and I would drill into, that OLake Iceberg. I think that's what we called it, test OLake, and then just to make sure I'm in the right place. Oh, nope, it's not test OLake. It's, what was the name of it? OLake test.
OLake test, yes.
Yeah, I went the other direction, and then it was Starburst, OLake. Hopefully that'll find the table. There it is. So you can set this up in a whole catalog or whatever, but I'm just going to target that one table, and I'm just going to say, look, I'm going to trust someone else to take care of this stuff. We didn't go into all the other maintenance types. We focused just on compaction, again, making fewer, bigger files. And why not let somebody run a tool here? So I'm just going to set this thing up and say, yeah, run this regularly, run it in this cluster. And then I'm just going to say, hey, maybe run it on the New York's time zone, East Coast. I'm not the worst cron tab guy, but I think I'll just show using it here. Let's say daily, using it at 2:30 in the morning. There we go. Done. That'll take care of it, all done, all through. Today, our tooling is, like you see, it's schedule-oriented. And that'll get you pretty far. Your biggest tables, your biggest whatever, I'm encouraging you to find that right sweet spot. In your most giant of tables, you might try to just say, hey, I might do this outside of an automated tool today. But if you have a lot of Iceberg tables, turn this on. It's going to get you really, really far. One less thing for you to have to mess with. And again, kind of get yourself there. Why don't I stop sharing my screen, and we'll see if there's any questions out there for me or from you, or hopefully that was somewhat entertaining or somewhat useful.
Yeah, sure. I'll just read out the questions for you.
Good.
So the first question is, can you discuss about trade-offs with respect to query engine using deletion vector versus the MOR, that is writing positional or equality delete strategy?
Yeah, I would say this. So those that know these deletes concepts. So when we do a merge on read instead of a copy on write strategy, then what do we end? So copy on write just says rebuild the files for the next version, move on. Most people are saying probably merge on read is the best way to solve updates as we go. And then missing the question, make sure I got it right here. Was it about deletion vectors? Will they help us? Or?
Yeah. So the question is, what is the trade-off between using a deletion vector versus an MOR strategy?
Well, I would say that's not a trade-off because we're going to do deletion vectors as part of MOR. Let me think about that real quick. So if you do copy on write, you won't need deletion vectors because you're going to rebuild. That compaction that we just did is somewhat equivalent to a copy on write, build it. So I would say this, deletion vectors or deletion, binary deletion vectors are referred to in Starburst and Iceberg 3 are this. When we delete today, so I've got 5 files here, 5 records. If I delete this finger here, I build a delete file. I'm sorry if I did an update. Let's do a delete. If I do a delete, number one, I have a new file with a deletion marker. It says that one. If I delete this file, then I'm going to build another file that says, oh, you go delete him. So we're building these positional deletes. I think I heard equality deletes, but let's focus on positional deletes. And then for fun, I built one more. So I'm down to the Mahalo kind of thing. I've got 3 other files, each saying whatever. So a deletion vector is going to be your best friend, and you're going to get it for free with version 3 there, is because what happens every time I delete this first one. Okay, I have one delete file, basically equivocally the same thing. When I delete this, for this new snapshot, instead of building another one, it's going to rebuild a better deletion file. So it's going to say that previous version needed this plus this. And then when I delete this, it goes, well, why don't I just append? It's not really appending, it's rebuilding. But he says, I got a better delete file that has 2 records in it now. Then it has 3 and it's 4. So it still builds one for each version. How does that help us? Well, it helped us a minute ago. We won't have 57 files. We'll have a smaller number of files because it's going to keep clumping those those deletes back up to a file together. It doesn't edit anything. It just rebuilds a better one. So at merge on read, we have fewer of those deletions to walk. It's going to see the same results, but fewer files for that. Hopefully that answered the question a little bit. So we're going to say that for every data file, we won't have more than 1 delete file per snapshot.
Yes.
That's the answer, yeah.
Okay. So the next question is, where do you see Apache Iceberg ecosystem in the next 2 to 3 years?
I think I personally, well, one, it will continue to be the standard kind of open source. I'm sorry, open platform. It's really the best way to say this. It's open source, sure, but open platform space. What you're seeing today is really good. The fact that I can run this and query different ones, I mean, that's only going to continue. What I think you see happening in Iceberg is, there's some things are like, hey, can we get better? Deletion vectors, great example. How do you get better? This thing called row level lineage, that's good for maybe incremental materialized views, things that we'll see better versions of the sooner. So all that kind of stuff that makes it better than what it already is, expect that to happen. Always does. What I also see happening, and I'm on the fence if it's good or bad, is that Iceberg usually you want your framework to take on more. And one thing we're talking about taking on in kind of the REST catalog is planning, things like query planning. So the engines do their own planning today. They ask a catalog, they find this metadata, then they say independently, Spark versus Trino says, how best can I solve that for me? If we want to have an outboarded system that says, hey, let me kind of build a logical plan for you, I don't know if that's the right answer or not. It's very interesting, but I don't know if engine providers are going to want that, so I'm struggling, in some ways. Is Iceberg going to tackle more than one? That's a great problem. That is a cool problem to solve more instead of less problems. I would say, so in general, I would just say, expect it to only be more pervasive, expect third parties themselves to behind the scenes leverage Iceberg. Postgres has some hooks around, hey, once the data gets so big, maybe I will behind the scenes start using Iceberg myself just to make things. So the adoption's only going to go up higher and faster, better. There's only going to be more performance for the things we're already doing. And then absolutely, there's this, could we do more? And again, I'm not trying to, people at the Iceberg spec and the team are doing all kinds of awesome things. The one that they'll tackle soon is the one that I think is important, which is to finish efficiently a 2-phase commit. Can I make a change to 3 tables at once and get one single snapshot that spans all that? There are a couple folks doing that, not in open source today, but look for Iceberg to solve that one for us. Today it's an auto commit, single operation commits, so single table, single operation. Look for two statements, 4 statements, 5 tables, to be one transaction. The fundamentals are all there. We're just basically doing the old school, what they did in databases 30 years ago, 2-phase commits. Everyone, the pre-commit, and then we are all ready. Yeah, let's do a final commit. So that's not that hard, but it is needed for a lot of us. So.
Okay, I think the next question is from Bernhard. It's for OLake. So OLake DB2 CDC. So Bernhard, DB2 CDC feature request. Yeah, you can create a feature request on the GitHub. Our product team will get back to you on it soon. And the Iceberg V3 support, we are having an internal discussion on it. We'll get back to you. And how many jobs at the same time can one create in OLake? So you can create any number of jobs in OLake, but make sure you also scale the instance or add job pod mapping if you are using Helm. Okay, so the next question is, what is the one thing you think data engineering teams consistently get wrong when moving to a lakehouse architecture?
Is that one you're going to tackle, or you want me to own it?
No, yeah, you can go ahead and answer it.
I think for folks that are truly new to the data lake, in other words, their data teams have been working in relational systems, they've been working Teradata as their OLTP and Oracle stuff. It's not special to data. It's not special to data lakes. It's special to every time we change technology, the technology acts a little different, which means we have to learn to understand why it's a little different. So these systems are not databases. So all the standard approaches and ideas and things you have, they're not always exactly the same. And probably one of the biggest ones that people hit, and I think most people get this already, is don't be so tied always to, hey, I used to do this OLTP system with a third normal form system, and I did my data warehouse with this star schema. Realize that maybe in general, under the covers, while these engines do really awesome things for joins and performance, things like the best join in a data lake is a no join. Look at flat, do a lot, be okay with, I've modeled the world for these technologies, so people take those same models and say it works just fine in this new system. It may not work just fine. So if that's your strategy, great, do some testing, make sure everything's looking good, but be okay or be open to expecting things are a little different. How do you solve it? Make sure on your team, you got one or more people that have kind of done that already. If that's hiring, if that's consultative help or something like that. But be open to saying, I know my business and I know my tooling, but I am changing something. So let me get some, let me not get someone to do it for me, but let me get someone that's done it and can give me some of those roadblocks and pitfalls. So that's really my biggest gotcha that I see.
Okay. Just a second. Okay. AI and data engineering are converging fast. Do you think the role of a data engineer looks meaningfully different 5 years from now?
Sad to say, I think it does in some levels for sure. No matter what, I mean, it's already a little different today, and we're still trying to figure these tools out for sure. I think probably it's going to change data analysis as much or more, mainly because for this to be well, the structure of the data, you hear a lot about semantics or context or the OSI, all these things. That good old fashioned, Lester made fun of modeling a minute ago. What I was making fun of was modeling that's so perfect that performance may bear. You can have denormalized worlds that still are very highly modeled and rigorous and are heavily articulated and documented. So I think the role is going to be much more of a data governance, a little bit of data librarian, I guess you can say in many ways. But yes, tooling will get easier and better. Well, I don't think we'll get away from anytime soon necessarily if someone say, yeah, that looks like the right thing to do. But the real way that and it's not about fixing it for data engineering, it's about the end user. If they want to be successful, they need to have answers that look about the same every time they get there. How do they do that? Meaningful context. So we're going to have to make sure we're using tools as data engineers that once data is loaded and ready for consumption, it is highly articulated, highly documented, highly, because that's what's going to make those dumb LLM systems work great when they go, here's all the stupid rules that explain these weird column names and by golly, these weird values inside of them. So I think we're going to transition and see ourselves as data czars, data governors, and there'll probably be fewer of us. There'll probably be more less technical, because to be the data czar, you need to know the data. So for those that have fortunately or unfortunately find themselves in the same job for 5 or 10 years or longer, you are better suited than a super technologist that doesn't know your domain. Why? Because you can explain what all that means. So that's my hunch. And I can't make any better predictions beyond that because I probably wouldn't have predicted we're even where we are today. If you went back 4 years ago, I doubt I would have gone, hey, here's exactly where we are. So it will change for 100% sure. Let's all stay frosty. But I do think, unfortunately, I think there'll be less of us, and that's not the worst thing, but it's, things are changing. People are moving our cheese, and we have to, I would also say don't be so foolish either way. So foolish to go, none of this will change. It's all noise. I'd love to be that grumpy old guy, but I also, also don't want you to be so excited that you're not thinking things through. So tools are coming, they're changing. We'll normalize them out, but it might take another 1, 2, 4, 5 years, but it will change 100%. And I do stand by what I said a minute ago. It's about that notion of semantics, context. So it's basically bring metadata around the structure, metadata around the weird field values, that kind of stuff. That's probably our job. We already do it today. We just hide it from everyone. We just do enough and then tell the BI guy, oh yeah, this means that, and everyone's happy. But for it to be successful in the front end, it has to be a human talking about their business, and then the engine's finding enough that context to feed a simple generic LLM and say, hey, give me an answer that will be the same tomorrow.
Yeah.
And not just noise, because we know it. The engines just try. They don't hallucinate. They just do their thing. Okay, I rambled too much on that one.
No, it was really informative.
Awesome.
I think that's all the questions we had. Yeah, that's all the questions we had for today. So, guys, you can follow our Slack community for OLake. Harsha's going to post it in the chat, and you guys can follow it there. We post all the latest features that come out for OLake. And if you guys face any issues with OLake, you can go ahead and comment in the help section there. So we'll be available most of the time to answer you guys and help you guys adopt to OLake as well. And Lester, you can also go ahead and promote Starburst here, so people get to know.
I'll be lightweight on it. I'll try to be nice. I already did my links and stuff. I'm a big fan of Trino. I'm a big fan of Starburst, not just because they signed my check, but I do believe in them. What I want to take my moment and say, hey, thanks for everyone that did dial in. Hopefully it was something useful. I always want, if I ask someone to spend some time with me, I hope they get something out of it. I know I got something out of it. I want to thank you guys at OLake, because we have talked about getting together a long time now, and it's been my fault for us not getting together any sooner. And so I'm happy, I'm blessed, I'm excited that we spent some time together and showed these tools off simultaneously all around Apache Iceberg. So thank you for inviting me. Thanks for having me.
Thank you so much, Lester. Okay, guys, I think it's time to end the webinar.
Always the funnest part to see who leaves the meeting first. I'm going to hit the leave. Thanks, everybody. Y'all take it easy now. Bye-bye.
Bye-bye.